Let's dive into space. Number 10. The ghostly light between galaxies. In the mid-1990s, as Hubble's instruments swept across the vast spaces between galaxy clusters, the data began returning something that stopped astronomers cold. Scattered through the darkness between galaxies was a faint, diffuse glow with no identifiable source. Not a galaxy, not a nebula. Light that appeared, by every measurement, to be coming from nowhere. What scientists expected to find in the spaces between galaxies was emptiness. The standard model of cosmic structure treated intergalactic space as a void, a backdrop against which the real action of galaxy formation played out. The regions between clusters were, in theory, dark. Hubble's deep imaging surveys of the mid to late 1990s were designed to map galaxy distributions, not to find something lurking in the spaces between them. What Hubble captured was a phenomenon now called intracluster light, or ICL. These were orphaned stars, billions of them, gravitationally stripped from their host galaxies over cosmic timescales and left to drift alone through intergalactic space at speeds of hundreds of kilometers per second. They were not connected to any galaxy. They belonged to nothing. They simply wandered, emitting their cold, faint light into a void that was supposed to be empty. The scientific implications took years to surface publicly. A landmark 2021 study by astronomers Mireia Montes and Ignacio Trujillo, published in the astrophysical journal Letters, revealed something even more unsettling. The distribution of this orphaned starlight traced the halos of dark matter with extraordinary precision, mapping the invisible scaffolding of the universe more accurately than any direct dark matter detection method previously attempted. Hubble had accidentally found a way to see the unseeable. There are more stars wandering alone in the darkness between galaxies than exist in entire galaxy clusters themselves, and Hubble had been photographing them for years before anyone thought to tell the world. Number 9. The ultraviolet puzzle of Andromeda. When Hubble trained its ultraviolet instruments on Andromeda, our nearest large galactic neighbor, at 2.537 million light-years from Earth, astronomers expected confirmation of existing models. What the data returned instead triggered a quiet, persistent debate that lasted years before reaching public discourse. At the core of the Milky Way's future collision partner was something that did not fit. Andromeda, also cataloged as M31, was considered one of the most thoroughly studied galaxies in astronomy. Its proximity made it ideal for testing theories of galactic structure and stellar evolution. Scientists believed they understood it. Hubble's ultraviolet observations in the early 2000s, using instruments capable of detecting radiation invisible to ground-based telescopes, were expected to refine existing measurements rather than produce surprises. What Hubble found was a bright, anomalous ring of ultraviolet emission at the galaxy's core, far more intense than stellar evolution models predicted. More disturbing was what lay at the very center. In 2005, astronomer Ralph Bender and his collaborators, using Hubble's Space Telescope imaging spectrograph, identified a compact secondary structure within Andromeda's nucleus, designated P3, a distinct stellar population orbiting the central black hole separately from the main nucleus. Andromeda did not have one heart. It had at least 3 distinct nuclear components, each behaving differently, each raising its own unanswered questions. The implications were difficult to frame in a press release. This was not a distant, abstract galaxy. Andromeda is the galaxy currently traveling toward the Milky Way at approximately 110 kilometers per second, on course for a merger in roughly 4.5 billion years. Hubble had revealed that the core of our approaching galactic twin was more structurally complex and less understood than any public briefing had acknowledged. If the heart of the galaxy heading directly toward us is already this poorly understood, what will we find when the two galaxies finally collide and their mysteries become our own? Number 8. The missing baryons. For decades, cosmologists working with Hubble's spectroscopic data faced a problem so fundamental it threatened the credibility of modern cosmology itself. Roughly half of all the ordinary matter that should exist in the universe, the atoms that form stars, planets, oceans, and people, simply could not be found. It became known as the missing baryons problem, and Hubble's instruments sat at the center of the search. The universe's total content of baryonic matter, the ordinary atomic matter described by the periodic table, is precisely calculable from the physics of the Big Bang. Measurements of the cosmic microwave background and Big Bang nucleosynthesis models agree on the quantity, but by the early 2000s, astronomers cataloging stars, galaxies, and gas clouds could account for only about half of what should be there. The rest had simply vanished from the observable record. NASA's response was direct. The Cosmic Origins Spectrograph, installed aboard Hubble during Servicing Mission 4 in May 2009, was specifically engineered to hunt for these missing baryons in ultraviolet wavelengths invisible to any ground-based instrument. The hypothesis was that the missing matter resided in the warm-hot intergalactic medium, a vast, diffuse web of gas filaments threaded between galaxy clusters at temperatures between 100,000 and 10 million Kelvin, hot enough to be nearly invisible, but traceable through faint ultraviolet absorption signatures that only Hubble could detect. In 2018, a study led by Fabrizio Nicastro using multiple space telescopes reported a detection consistent with WIM filaments, offering what many called the first observational confirmation. But the full scientific consensus remains contested, with subsequent studies debating the robustness of the signal. The missing matter may have been found in principle. Whether it has been found in practice is still an open question. For 20 years, science textbooks described a universe where half the matter was simply missing, and Hubble's ultraviolet instruments had been pointing toward the answer the entire time. Number 7. The protoplanetary disks of Orion. In 1993, following the first servicing mission that corrected Hubble's famously flawed optics, astronomers directed the newly sharpened telescope toward the Orion Nebula, one of the most active stellar nurseries in the galaxy. What came back from the cameras was extraordinary. Embedded within that vast cloud of gas and dust, 1,344 light-years from Earth, Hubble had captured something no telescope had ever clearly resolved before: the raw, chaotic machinery of solar system formation. The Orion Nebula, cataloged as M42, had long been studied as a region of intense star formation. Astronomers expected to find young stellar objects surrounded by disks of gas and dust, the theoretical precursors to planetary systems. The prevailing models suggested this process was gradual, relatively stable, and predictable. Hubble was expected to provide sharper images of a process that was already reasonably well understood. Astronomers see Robert Odell of Rice University analyzing Hubble's wide field and planetary camera. Two imagery identified more than 150 protoplanetary disks in a single field of view. He named them ProPleds, short for protoplanetary disks, and the images were genuinely remarkable. But the remarkable part was not their existence. It was what was happening to them. The massive nearby star, Theta 1 Orionis C, was bombarding these nascent solar systems with intense ultraviolet radiation, evaporating their planet-forming material at catastrophic rates. Some ProPleds were estimated to be losing mass so rapidly that their disks could be destroyed within 100,000 years, a geological instant in cosmic terms. Hubble had not photographed the peaceful birth of solar systems. It had photographed their violent, ongoing destruction in real time, processes stripping away the raw material of potential planets before those planets could ever form. If Hubble showed us solar systems being torn apart before they could fully assemble, how many chances at life has the universe already destroyed in the time it has taken us to find them? Number 6. The oldest light Hubble ever captured. Between September 2003 and January 2004, Hubble's advanced camera for surveys stared at a single, unremarkable patch of sky, roughly 1/13 the diameter of the full moon, for a cumulative total of 11.3 days. The resulting image, released publicly in 2004 and named the Hubble Ultra Deep Field, contained approximately 10,000 galaxies. It became one of the most reproduced photographs in human history. What the press release did not emphasize was what the data showed at the very edges of that image. The ultra-deep field was presented as a triumph of observation, a record of the universe as it existed across almost its entire history. The public-facing narrative was one of discovery and wonder. Astronomers were largely satisfied with that framing. The image was extraordinary by any measure. What required more careful explanation were the objects at the greatest distances, galaxies as they existed approximately 800 million years after the Big Bang, during a period astronomers call cosmic dawn. Several of these earliest galaxies appeared wrong. They were too structured, too massive, too mature for their age. The models of galaxy formation that had been developed and refined over decades predicted that galaxies at this epoch should be irregular, small, and chaotic, the raw beginnings of structure rather than the organized systems Hubble was imaging. The problem was not trivial. In 2012, the follow-up Hubble Extreme Deep Field extended the anomaly further, capturing galaxies 13.2 billion light-years away in configurations that lacked satisfactory natural explanation. Scientists were aware of this tension for years. The impossibly early galaxies problem was documented in peer-reviewed literature from the mid-2000s onward, acknowledged in academic circles while absent from most public-facing communications. It was not until the James Webb Space Telescope confirmed and dramatically amplified the anomaly in 2022 that the problem became front-page news. The galaxies at the edge of Hubble's deepest image had been quietly contradicting our model of the universe since 2004, and it took 18 years for the scientific community to decide the world was ready to hear about it. Number 5. The strange behavior of Eta Carinae. Approximately 7,500 light-years from Earth, in the heart of the Carina Nebula, a star has been threatening to die for over a century. Eta Carinae is one of the most massive and luminous objects in the Milky Way. A hypergiant estimated at between 100 and 150 solar masses, and burning at a rate that makes its eventual destruction not a possibility, but a certainty. When Hubble turned its instruments toward the aftermath of its last great eruption, what came back was more alarming than the official communication suggested. In 1843, Eta Carinae underwent what astronomers now call the Great Eruption. For a brief period, it became the second brightest star visible from Earth, reaching an apparent magnitude of approximately -1, outshone only by Sirius. It did not explode. It survived. The eruption ejected several solar masses of material, forming the twin-lobed structure now called the homunculus nebula, each lobe roughly half a light-year across, expanding outward at over 600 kilometers per second. What caused an eruption of this magnitude without triggering a full supernova was, and remains, unexplained. Hubble's detailed imaging of the homunculus, conducted from 1995 onward using the Wide Field and Planetary Camera 2, revealed structural asymmetries in the ejected material, suggesting the 1843 event was more directional and more violent than contemporary models predicted. Subsequent Hubble data also confirmed the existence of a binary companion, Eta Carinae b, with an orbital period of approximately 5.54 years, first proposed by Augusto Daminelli in 1996. This companion's gravitational influence complicates every attempt to predict when the primary star will finally detonate. The critical detail, handled carefully in scientific literature, but rarely emphasized in public briefings, is that Eta Carinae is classified as a luminous blue variable, a category of star considered intrinsically unstable. A full hypernova or collapsar event could, under certain geometric conditions, produce a gamma-ray burst. Current modeling suggests the star's rotational axis is not aligned with Earth, which would significantly reduce, though not eliminate, any potential threat. Eta Carinae has been on the edge of detonation for over a century, and Hubble's images revealed just how thin the margin between stability and catastrophe truly is. Number 4. The dark structures in the Coma cluster. In 1933, Swiss astronomer Fritz Zwicky analyzed the velocities of galaxies within the Coma cluster, a dense collection of galaxies approximately 320 million light-years from Earth in the constellation Coma Berenices, and noticed something that would change cosmology forever. The galaxies were moving too fast. There was not enough visible matter to account for the gravitational forces holding the cluster together. Zwicky proposed the existence of invisible dark matter, a term he used decades before it entered mainstream science. Decades later, when Hubble examined the same cluster in unprecedented detail, it found proof that the story was far stranger than Zwicky had imagined. Beginning in the early 2000s, Hubble's imaging revealed an unexpected abundance of enormous, ghostly structures within and around the Coma cluster. These were ultra-diffuse galaxies, objects the size of the Milky Way, but containing only about 1,000th as many stars. They were barely there. Vast in extent, but almost entirely transparent, they seemed to be held together by something other than the stellar mass that defines ordinary galaxies. In 2015, astronomer Peter Van Dokkum of Yale University formally identified 47 of these structures in the Coma cluster, using imaging that depended on Hubble data for confirmation. Then the picture inverted entirely. In 2018, Van Dokkum's team announced the discovery of a galaxy designated NGC1052-DF2, identified using Hubble observations, that appeared to contain almost no dark matter at all. Where the ultra-diffuse galaxies seemed to be made almost entirely of the invisible substance, this galaxy appeared to be missing it completely. The finding was contested, with a 2019 counterstudy by Ignacio Trujillo arguing the galaxy's distance had been miscalculated, but the debate itself illustrated the problem. Within the cluster that gave us our first evidence of dark matter, Hubble had found objects that shattered every assumption about how dark matter behaves. In the same region of sky that told humanity dark matter existed, Hubble captured evidence that we have no idea how it actually works, and that finding has been deepening, not resolving, ever since. Number 3. The Hubble tension. In 2001, after a decade of painstaking observation, the team behind the Hubble Space Telescope Key project published what was supposed to be a definitive result. Led by astronomer Wendy Friedman, the project had used Hubble to measure the distances to galaxies across the cosmos, calibrating what is known as the Hubble constant, the number that describes how fast the universe is expanding. The value they published was approximately 72 kilometers per second per megaparsec. It should have been the final word. Instead, it was the beginning of a crisis. The Hubble constant is not merely a number. It is the pulse rate of the universe, the single measurement that underpins our understanding of cosmic age, structure, and fate. For the standard model of cosmology to hold together, every method of measuring this constant should produce the same result. When the European Space Agency's Planck satellite measured the same quantity using the cosmic microwave background, the relic radiation from the Big Bang itself, it returned a different answer, approximately 67.4 kilometers per second per megaparsec. The two values did not match. This discrepancy became known as the Hubble tension. The gap between these measurements might seem small, but statistically it is devastating. By 2022 and 2023, analyses by the SH0ES team, led by Nobel laureate Adam Rice of Johns Hopkins University, had confirmed the tension at a statistical significance of 5 sigma, meaning the probability of the discrepancy being a random error is approximately 1 in 3.5 million. This is not a rounding error. This is not an instrument calibration problem. Rice himself has described the tension as potentially requiring new physics, a phrase that, in the language of science, means the existing framework may be fundamentally broken. The universe appears to be expanding at 2 different speeds simultaneously, depending on whether you measure the early cosmos or the late cosmos. And the instrument at the center of that contradiction is the telescope we named as our greatest eye on the sky. When the most precisely calibrated space telescope in human history produces a measurement of the universe that is statistically impossible to reconcile with itself, it does not mean we measured wrong. It means something about the universe itself is not what we thought it was. Number 2, the dimming of distant supernova. In the mid-1990s, 2 independent teams of astronomers aimed Hubble at some of the most distant explosions in the observable universe. Their goal was straightforward: measure type 1. A supernovae in far galaxies use their known brightness as cosmic rulers and calculate precisely how fast the universe's expansion was decelerating due to gravity. Both teams were confident they knew what they would find. The data returned from Hubble proved them catastrophically wrong. Type 1. A supernovae were considered the most reliable measuring tools in cosmology. Standard candles that always ignite at the same peak luminosity, allowing astronomers to calculate distance with precision. The High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, and the Supernova Cosmology Project, led by Saul Perlmutter, were operating independently, using different methodologies, checking each other's potential errors without coordinating their conclusions. The universe's deceleration rate was the question. Both teams expected an answer consistent with existing models. The supernovae were too dim, not slightly dim, measurably, undeniably, consistently dim across dozens of independent observations, which meant they were farther away than they should be, which meant the universe was not decelerating. It was accelerating. Something unknown was pushing the fabric of space itself apart with increasing force, working against gravity across every scale, in every direction, with no known physical mechanism. This force was eventually named dark energy. It constitutes approximately 68% of the entire universe. Before the late 1990s, no one knew it existed. Both teams spent months examining their data for errors before accepting what it showed. The announcement came in 1998. Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics in 2011. The discovery was real, confirmed, and world-altering. But for a period of nearly 2 years, small groups of astronomers held Hubble data proving that an invisible force comprising most of the universe was tearing space apart at an accelerating rate, and the world was not yet told. The most consequential discovery in the history of cosmology sat inside Hubble's data for nearly 2 years, understood, verified, and carefully withheld while its discoverers searched for any explanation other than the one the numbers demanded. They never found one, and the universe has been accelerating toward its own dissolution ever since. Number 1. The void at the edge of the observable universe. Deep in the southern sky, in the constellation Eridanus, there is a region of space that is colder, emptier, and more structurally anomalous than anything physics has been able to explain. It was first identified in data from NASA's Wilkinson Microwave Anisotropy Probe in 2004, with analysis published in detail by 2005 by researchers including Pablo Vielva and colleagues. It appeared as a vast region of the cosmic microwave background, the relic radiation of the Big Bang, that was approximately 70 microkelvin cooler than its surroundings. In the mathematics of cosmology, that difference is enormous. It became known as the CMB cold spot, and for years it sat in the data, like a question no one wanted to fully answer. The cold spot is not a subtle artifact. Statistical analyses confirmed its anomalous nature repeatedly, and the search for a physical explanation became one of the quiet obsessions of early 21st century cosmology. The leading candidate emerged in 2015 when astronomer Istvan Chaput of the University of Hawaii and his collaborators identified what they called the Eridanus supervoid, an immense underdense region of space spanning approximately 1.8 billion light-years, one of the largest known structures in the observable universe. The supervoid, they argued, could produce the cold spot's temperature signature through a mechanism called the integrated Sachs-Wolf effect, as photons of light lose energy passing through regions of depleted matter. Hubble's contribution was critical and quiet. Its deep-field galaxy surveys provided the observational data on galaxy distributions that allowed the supervoid's boundaries to be mapped. Without Hubble's decades of accumulated imaging, the three-dimensional structure of the void could not have been confirmed. But confirmation of the supervoid created a new problem rather than solving the old one. When theorists calculated how much temperature depression the supervoid alone could produce, the number fell short. The cold spot was colder than the supervoid could account for. Something else was contributing to the signal, and no known structure within the observable universe could explain what it was. This is where the science becomes difficult to frame in a press release. Laura Mersini-Houghton of the University of North Carolina, building on work in multiverse cosmology, proposed a hypothesis that the data did not contradict. That the CMB cold spot is a bruise, a physical imprint left on our universe during the inflationary epoch when a neighboring universe pressed against our own and the two pulled apart. Under certain theoretical frameworks derived from string landscape cosmology, inflation would have produced a vast number of parallel universes, and the boundaries between them, regions where one bubble cosmos influenced another during the first fractions of a second of existence, would leave precisely this kind of cold, anomalous scar on the cosmic microwave background. Mersini-Houghton published this hypothesis, defended it in peer-reviewed venues, and the data has never disproven it. The multiverse hypothesis remains officially unconfirmed. Most cosmologists prefer to wait for further data, but the supervoid alone does not close the case, and the cold spot remains in the data, colder than it should be, larger than it should be, sitting at the edge of everything Hubble and its sister instruments have ever observed. Hubble may have spent decades helping to map the fingerprint of another universe pressed against our own at the moment of creation. The data has always been there. The mathematics has never ruled it out. And the silence of the cosmos at that precise coordinate in the southern sky remains the most profound thing our greatest telescope ever failed to fully explain. If you want to see more videos like this, click the video on screen now and make sure to subscribe.